Okay, hi everybody. Thank you for coming, and sorry for not putting up an abstract for this talk. I didn't do it to be mysterious. I did it just because I was added to the schedule at the last moment, like the guy who has to come out of the stands at the Blackhawks game to sort of suddenly be like the goalie because the other two goalies were injured. And so, not having an abstract, I fear that this title is maybe in retrospect like a little bit grandiose. So I'm not going to sort of like answer this question in full or even really answer it at all. This is maybe going to be a little bit more like a sort of uh, personal account of some of my own experiences as a pure mathematician, like working with machine learning tools and sort of some thoughts um, about what this is good for in math. And also, Mike asked me because this is a math institute where we're in these 2 days, we're having a lot of talks about interesting stuff going on in the sciences more broadly to sort of talk about what are the differences that we see between the way this material plays out in pure math versus the way it plays out in science. So I encourage people to sort of jump in when they see, I'll point to some differences, but I encourage people to jump in to say like, biology is not like that, or what have you when I say certain things. So let me start as I sort of narrow the scope to sort of say some of the things I'm not going to talk about today that could be talked about under the ambit of such a talk. In particular, I'm not really going to talk about theory of machine learning and what mathematics has to offer machine learning, but this does give me the opportunity to advertise for the locals that there's going to be an extremely interesting sounding workshop next week, which I cannot stay for, but about geometry and machine learning. Well, you will hear a lot about very interesting people from mathematics thinking about what we can actually say about the geometry of what's happening inside the box. And another thing I'm not going to talk about so much today is like, why don't we simply converse with an LLM or a swarm of LLMs or sort of anything about how to solve our math problems? That's an oversimplification of something that people will believe will work, but I do want to emphasize that there are two somewhat distinct, although they overlap, ways of thinking about this problem of generating material of mathematical import and interest from machine learning. One way is that mathematical reasoning and mathematical work will sort of come sort of as an epiphenomenon of more general reasoning capacities. And I think that's like a super interesting line of work. It's just not what I've worked on, so I'm not going to talk about it. I'm going to actually talk about the sort of a different line of work where you sort of really build more bespoke systems that are aimed at solving very specific mathematical problems. And certainly those two lines of thinking are not completely distinct, and they can work in concert with each other. I just want to, comment that that's not the direction that I'm going in today's talk. So one sort of somewhat parallel question. I think Noam brought this up as parallel yesterday in the panel. Okay, I wonder if I can like change that. I apologize for these weird like little things to say click. It's probably in the wrong view if you want to change that. Oh, that's much better. Okay. Oh, does that mess it up for the Zoom people? Okay.
We have to reshare.
We should do whatever is good for the people walking on Zoom, even if you guys have to look at my.
Are currently sharing. So previously it was just a window.
Okay. If anybody's watching the Zoom, quickly text Mike to say I can't see it if you can't see it. Okay. Yeah. So here's a sort of somewhat salty question that you could ask. This is like one of the many photos of the dejected-looking Go player that you can find on the internet nowadays. I actually am not so fond of this analogy. I don't think that math is so much like Go, but the analogy certainly has some meat to it, and I want to emphasize that certainly something like AlphaGo learns Go from the rules. It learns Go by extensive self-play, starting from complete scratch, which is why one version of it is called AlphaZero. It does not work by reading lots of books about Go and interpreting the words that people have written about Go. It doesn't work by like reading lots of recorded games of people playing Go. Those would actually be completely reasonable strategies. I just, in practice, and people can back me up if they know, I think those just don't work nearly as well. What do you think? Can you back me up? Can you back me up?
It's not AlphaGo goes to exact. AlphaZero adopted from scratch.
Oh, so I wrote it wrong. I should have said AlphaZero learns Go. Okay, thank you. This is why it's good that we actually have a workshop. Okay, so please, everybody mentally replace AlphaGo with AlphaZero, because that's what I'm talking about. But that works much better, right?
Yes.
Okay. So in some sense, the spirit of the work I'm going to talk about today is in that spirit of sort of like trying to get mathematical stuff, not by reading lots of math papers, although there's definitely lots of evidence that that's going to be productive too, but by sort of like working directly from the rules. That being said, what?
What are the rules of mathematics?
Depends what kind of mathematics you're doing. So I mean, yes, this leads into my next slide, which is that the big difference is that, math is not a game. I mean, we could fight about this, and maybe there's sort of some hardcore Hilbert people who would like disagree with me about this, but I would say most working mathematicians do not think that math is that much like chess or that much like Go. It is not a purely formal game with rules, but it does have games embedded in it. You can't deny that there's sort of something gamish about it. And so there are at least two examples that we could talk about. One game is the kind of Hilbert game of like make a formal proof using formal rules of deduction. So yet another thing I'm not going to talk about is this wonderful world of like Lean and Cock and like other formal mathematics operations where you're trying to, in some sense, like learn a path in proof space using these formal operations to get from a desired statement to a desired hypothesis. Oh, does it look bad the way I'm doing it?
It's showing sample.
Oh, that's for the people on Zoom. They can see my notes. It's okay. I have no secrets.
Some people don't like it.
I don't have any like really big reveals in this talk that will be ruined if people can see the notes. It's okay. So what I'm going to talk about a little bit more is the make an interesting example game. And I'm going to specifically, most of the math I'm going to talk about today, even though I'm a number theorist, is combinatorics. And in combinatorics, one of the things you're trying to do, if you're trying to sort of solve some optimization problem, is you're trying to create an example of something that's as big as possible, satisfying certain constraints. That's a game. It has very definite rules. I just told you what they were. It should be as big as possible, and it should satisfy some list of constraints. So let me give you an example of a sample.
Comment.
Yeah.
A very, very common thing in mathematics, maybe more common than that, is here are the rules, find a counterexample.
Yes, you're way ahead of me.
Oh, okay.
So yes, one thing, I forgot if I put this on the slide, but like a counterexample is a good example of an example. And those are some of the most interesting ones, so we're going to talk about that. Okay, so let me sort of show you a sample problem that I love. So here are some pictures. These are pictures of dots on a grid. On the left, you have a picture of dots on a 6x6 grid, and on the right, you have a picture of dots on a 7x7 grid. I think it's like pretty hard to notice what's special about these grids, to be honest. So I'm just going to tell you what's special about them is that no three of these dots form an isosceles triangle. I will leave it to you to sort of check that visually, but you can try to find one and you won't find one. And in fact, as it happens, and this is not machine learning, this is not too hard to check by exhaustive search, these are the largest configurations in the 6x6 grid and the 7x7 grid, which have no 3 points containing an isosceles triangle. And already here, this is a completely open question. If I ask you on the n×n grid, how many dots can I put on it so that no 3 form an isosceles triangle, we have no idea. And in fact, not only do we have no idea, there's like a massive gap between the best one we can build and the upper bound given by the best one we can show doesn't exist. This is the kind of problem I think I get most excited about machine learning being used for. The problem is where human mathematicians have really like not gotten any grasp on what's actually going on. This is a problem. It's a funny problem because it's exactly the kind of question that Paul Erdős certainly would have asked, but we can find no record that he ever asked it. He asked a lot of things like this, but it sort of seems to be like somewhere in the convex hull of all Erdős problems, but not actually to be an Erdős problem. I think we just made it up a few years ago, and there is not like a long history of it, but it's a very good sample problem for this kind of thing. Maybe I'll show you sort of one bigger one, which was produced by machine learning. This is the biggest subset of the 52 by 52 grid that we know about, but we definitely don't have any proof that this is maximal, but this is the biggest one that our machine could find. And I just want to say a bit now about how one can use modern machine learning methods to build examples like this. And one thing I'm going to do, let me be honest, I'm going to talk about a few different pieces of work which tend to work on different problems. I'm slightly going to elide the differences between them on the extremely small chance that any of you have ever looked at any of these papers. Like, you'll be like, but I thought that paper was about this problem. Okay, yes, I'm going to use the isosceles triangles as a running example because it's you know, a lot of combinatorics takes place in very high dimensional spaces, which are very hard to put on a slide. The no isosceles problem takes place in 2-dimensional space, which is very PowerPoint friendly. So I'm going to sort of, if it's okay, sort of pretend that all of these papers were about the problem of finding large subsets of the grid with no isosceles triangles, even though they're actually about a whole suite of different problems. Because it's the main ideas I'm trying to emphasize today have nothing to do with the combinatorics of this particular problem. They just have to do with how we approach optimization problems like this from these methods. So just to sort of show you what work I'm going to talk about, this is a paper that I wrote with a group of folks at DeepMind that came out at the end of 2023 using a protocol called FunSearch, which is probably, that's what I'm going to tell you the most about today, because I think it has a lot of interactions with things that we have already talked about at both this workshop and yesterday's. This paper does not have anything about isosceles triangles in it, though, so maybe I will also mention the diagrams I just showed you are from a different project called Pattern Boost, which I worked on with François Charton, who was at Meta and is now at Axiom, Adam Wagner, who was in academia like me and is now at DeepMind, and Jordy Williamson, who will sort of be also in town for some of these materials, who's one of the really sort of has been one of the earliest real cheerleaders for machine learning applied to pure math, especially in combinatorics and algebra. So he's one of the people who got me into this area, along with Adam. And maybe I will really not talk about this at all, but I will just, to make it clear that this was sort of not a one-and-done situation, this is Alpha Evolve is a paper that came out of DeepMind in May 2025, which is in some sense a successor to FunSearch and has a lot in common with what I'll talk about FunSearch. I'm not on this paper, by the way. This is like a DeepMind enterprise. And which also has sort of some features in common with Pattern Boost as well. So this is certainly, this style of approach to machine learning and mathematics is certainly a very active concern. It's one of the threads. Yeah.
Like 25 years ago.
Yeah.
Is experimental mathematics, forget machine learning, like a well-accepted thing in mathematics now that in a way it wasn't like 25 years ago, or?
Yes, I mean, so I would say even 25 years ago, it was already pretty accepted, but definitely way more than 50 years ago. How about that? Because I would say 25 years ago, I was, I guess I was I still a grad student? No, not quite anymore. Anyway, whatever. I was more at the beginning of my career, and then, I mean, maybe no one can speak to this better than me. I would say.
Tell you an anecdote. So one of the older people here.
Okay.
Very quickly. What? 30 seconds. In 1970. I was a grad student in the Cambridge University Mathematics Department, and the guys here are going to find this hard to believe. I think I was the only person in the pure math department who could program a computer.
I don't find that hard to believe. Because my dad was a statistics graduate student here in the late 60s, and I think like almost nobody could program a computer then. Did you use cards? My dad used cards.
No, we actually used an interactive terminal, which was pretty advanced at the time. And
I hadn't come to Harvard yet, obviously. It was
I had a similar terminal type, and it was a tab type, of course.
Remember that there are experimental mathematics are experimental mathematics for a computer. There's a famous story of the wordless talk that's factor 2 to the power 67 minus 1.
Yeah, I mean, so that's actually, Noam makes a great point that computation in math has been going on, as a part of math, has been going on a lot longer than there were computers. Yes, exactly. So I mean, we have been doing computations to sort of like get ideas about things in a way that is not the sort of what you may think of as, if you think that math is an enforced path and all we do is deduce things from axioms, oh my God, no, we're so much more fun than that. Okay, yeah.
The counterexample is a counterexample. Doesn't matter how you get it.
Yeah, exactly. Yeah, so that's a good, right, it's a great point, a counterexample. And in fact, okay, let me say that I think I didn't put this on a slide, so a good chance to say it. I said I was not going to talk about constructing of formal proofs in this talk, but I am, because a counterexample is a formal proof of the falseness of a proposed statement. That's like a very specific species of formal proof, but it definitely is one. If somebody conjectures that there's no subset of the grid of size this many hundreds with no isosceles triangles, and I give you one, that is a formal proof that that statement was incorrect. So that's not the kind that Lean makes, but it is one. Okay, so let me say something about what FunSearch is, because it's a very strange idea which came from inside DeepMind that I did not think was going to work, and it works pretty well. So I think that's pretty neat. So fun is for function, but it's also fun. I think it was meant as a kind of pun, but it is, I got to tell you guys, very fun. Maybe I'll try to convey that as we go, but it stands for function. So maybe just to go back and say, the thing as a mathematician that you might think that you're going to do is somehow search the space of subsets of the grid of a given size. But then you quickly observe that you're not actually going to do that, because for those who have ever thought about this kind of combinatorial problem, there's like way too many, like way too uncomputably many. And then you think, well, maybe I'll sort of search some space of functions and sort of put a dot where the function is above 0 and not where it's below. I mean, you could do lots of stuff like this, and I just want to emphasize that despite fun standing for function, that's not what FunSearch does. Instead of searching directly for subsets of the grid, it searches the space of Python programs, which it then runs and sees if they produce a large subset of the grid with no isosceles triangles in it. I think that's a very weird thing to try to do, but A, it kind of works, and B, I'm going to kind of tell you a little bit about sort of the benefits that this approach has. So I'm going to do that by the way, first of all, since we're talking about the geometry of machine learning next week, I will emphasize that I'm being somewhat tendentious by using the word space here, because what the hell do I mean? As a mathematician, if I say the word space, if I invoke the notion of geometry, I should be saying that I have some notion of what it means to perturb, what it means for two programs to be close to each other. I don't really, not in any formal sense, but I also sort of want us to think of it as if we had some notion of that, because in some sense, the part of what's happening in the machine learning is that it in some sense provides us with some implicit notion of what that means, even though we don't actually have a well-formalized notion of the geometry of Python programs.
Are you already constraining the Python programs so that they do produce a subset of it?
So I haven't, in this talk, I'm going to say as much. So short answer, yes. Long answer, I'm going to say as much about the implementation as people want me to say, unless that's more than I know, in which case I'll say as much as I know. But yes, there's lots of constraints, and I'm going to tell you at least one of them I have slides for, and I'm happy to say more. So yes, when I say this, we're not actually searching the space of every Python program that could possibly exist, or every string of characters that could possibly exist that you might try to run as Python code. To get it to work, you have to constrain it through a channel. And that's an art, and that's what the people who work at DeepMind do. I definitely don't do that. So here's the cartoon. This is kind of the most important slide that sounds exactly like how this works. So here's what you do. You start with 1 million Python programs. Where do you get them? They're basically random. So already there's something very weird about that, right? Because if you just take a long chunk of random characters and try to run it as a Python program, it will not work, even if you have 1 million. I promise 0 of them will work. So in fact, I should say that already there's a skeleton program, and you have sort of, you start with sort of some seed of programs that do output a subset of the grid. They're constrained to do that. You give them nothing about isosceles triangles, but they are forced to be Python programs that generate some subset of the grid. Okay, so now you have 1 million of those. That's not that hard to make. Then you run them all. And most of them are probably, if you have a random subset of any large size, it's probably going to have an isosceles triangle in it. If this were a math talk, we could sort of talk about how you would estimate that, but it's not, so we're not going to do that. But some of them won't have any isosceles triangles. They'll probably be pretty small sets, but some of them will be. You throw out all the ones that fail and keep all the ones that are valid, keep all the ones that produce an example of the kind of thing you're looking for an example of. And then of those, you take the 100th biggest one. So you've sieved down from your very large set of 1 million problems to a very small set of 100 programs. Now, by the way, maybe I should say, do I literally mean 1 million? No. Do I literally mean 100? No. There's there's a big number and there's a small number, and you sort of hyperparameterize and make lots of choices and then try with other choices. And I don't even, if I'm honest with you, remember what these numbers actually are, because I drew this cartoon a long time ago. And then if you're familiar with like genetic algorithms, like actually this is happening in parallel and like a lot of different little islands so that you maintain diversity. So there's lots of this kind of stuff that I think is not the main point of what I want to talk about today, but I'm happy to talk about it if people want to. But in any event, you have 100 Python programs which maybe do slightly okay at generating slightly big subsets of the grid, which have no isosceles triangles. And then you feed them to your favorite code generating large language model and say, give me 1 million Python programs which are like these. And then again, because this is in genetic algorithm world, really what you do is you sort of join them in pairs and give 2 at a time and say, 1 million times, give me one that's like the child of these 2 or like something like that. And this is the part, by the way, where I say, whatever the notion of a space of Python programs is, because if you give me 2 Python programs, I don't know what the Python program is that's midway in between them. If they were actually on some manifold, maybe I would know that. But I don't. But this is what LLMs are really good at, right? This is a query that you can actually send to an LLM, and then now you have 1 million programs again. And now you just do this for like a long, long time. And if you're DeepMind, you have like lots and lots and lots of computers, and you can run it for, and I don't have to worry about how much it costs or how long it takes or anything like that. It just goes around and around in a loop for a long time. Are you skeptical this would actually work? I was too.
So genetic algorithms are amazing. But
Okay.
Is the selection criteria really important that it's 0, or do you say least, or I'm curious about hard versus soft selection criteria.
Such a great question. In this particular example, we used the hard criterion where we threw it out if it generated an isosceles triangle. We did not allow it to.
Do you know if it's important?
There are other problems. So there are other problems where you do better with a soft criterion. So just if people haven't thought of this, another thing I could do instead of my best performers all being valid examples that actually were examples, I could say, you know what? I'm going to forgive you. The set's really big and there's one isosceles triangle. I'm going to forgive you for that. I'm going to have some trade-off where I punish you for having isosceles triangles and I reward you for being big. That would be another way to do it. On this problem, we did the hard constraint, but there's
right? You have a big configuration, you've got one isosceles triangle, I delete one of the points in the triangle. Now I've got a pretty big configuration at work.
yeah, so you just started writing pattern boost because that's what pattern boost does. yeah, so that's in pattern boost. That's not in this. Yeah.
I don't to my own horn, I certainly didn't do anything I call AI. But when I was a cryptographer, I did a lot of combinatorial search. And sort of various heuristics like this was certainly don't my Python code, but it sort of vaguely feels the same way.
Yeah, so I want to emphasize that in some sense, this cartoon, this is not novel for people in optimization. The novel part is that you use an LLM for this step to do the mutation and to do the mating. That's the novel part. The overall structure of this is a genetic algorithm. I don't want to make it sound like this is like a novelty. There's like there's decades of technique that you build into this. But now I want to sort of just talk about what's downstream from this. Now that I've shown you the cartoon of how it works, let me say something about what's downstream of this. So one thing is that this came up in Marcus's talk just at the very end. It was a very nice lead-in to my talk because there was this question of like, well, the problem with large language models, or one problem with them, is that they give wrong answers a lot. Right? They hallucinate a lot. They say things that are trash. They give a lot of programs that don't run. Right? They give a lot of things that aren't Python programs. In a lot of applications, that's like a serious problem. But here it's completely not, because let's focus in on this like rightward arrow. This part has no LLM in it at all. So we're working with problems where if I give you a putative example of the kind of thing you're looking for, I can check extremely cheaply, extremely fast, and extremely reliably whether it is an example or not. And I can assess it, and I can like evaluate it and count its size. So this hallucination problem, which I admit is like a big problem in lots of applications, is completely not a problem here because it can generate 99.99% trash, and that's fine. I just throw all those out because I have a reliable trash detector. So that's, I think, one sense in which we talked about this question of how math applications are different from other science applications. I think it's not unique to math, but it's much more characteristic of math than many other areas. This fact that we can very, very swiftly take out the trash inside the loop like this. Yeah, Mark?
But these algorithms, is it a situation where each algorithm is producing like one configuration and the grid size is fixed? Or are you trying to get a grid of different size? Or is the algorithm deterministic? Is it probabilistic? What's exactly the set have?
Okay, so I'm going to say something about training on one size and going to another. That's like another paper that I wrote with Drew and my student Karan, which I think I forgot to put the picture of it in the slide, but like
But for your question.
for this one, there's a fixed size.
Right?
Yeah, for this one, there's a fixed size. And it's and
The algorithm produces just one configuration.
each algorithm produces just one configuration. That's right. I decided to do this. How many slides from now? Just in a few slides now, we're actually going to see how this works. So you'll see more like what this actually looks like. Okay. Oh, right. So a difference in science, right? If we sort of produce like a million putative molecules that we think are going to be therapeutic from a disorder, it would be great if without doing a physical experiment with people or rats or whatever, we could just know which ones were actually like lethal toxins. But we don't. We just like give them to lots of people and see if they die, right? Or like something like that. I don't know that much about clinical trials, but it's like something like that, right? And that's very expensive and time consuming. So we don't have to do that.
But now we can just ask ChatGPT what it is.
Yeah. Okay, but then there's LLMs in this arrow, right? So I want there to be no LLM in this arrow. Okay, so one important observation I do want to say is that this actually does work in some cases. So here's the one place where that paper with DeepMind, we were working on a problem called the CAPSET problem, which is one I worked on a lot as a pure mathematician, which is part of the reason I was involved in that project in the first place. And it did find in 8 dimensions. That's a sort of 8-dimensional space over a finite field. It's hard to put on the board. That's why I didn't use it as my running example. But it did find one that was bigger than any that a human had made. And that's a problem that has a pretty long history, that people have been thinking about it a long time. So that I was, to be honest, like somewhat surprised that this worked. And there's AlphaEvolve has sort of some long list of like 30 to 50 other examples in combinatorics where best known human bounds have been sort of incrementally improved by these kinds of methods, but not on subsets with no isosceles triangles, by the way. There we still haven't beat it. So let me tell you something now. This is the audience participation portion of the talk, because I want to emphasize that these programs are even more constrained than I've told you. They're extremely tightly constrained, and here is what they actually do. In FunSearch, I think in AlphaEvolve there's a little bit more freedom, but here is what the way a program like this would actually work. Here's a 3x3 grid. We're going to try to make a subset of it that has no isosceles triangles. That's one we can kind of do in real time. The program doesn't really output a list of points. All the program does is learn a real valued function on the points of the grid. So in this case, that's to learn like 9 real numbers. And what it does, now we're going to sort of basically make our set by doing a greedy algorithm. And the numbers, the function that FunSearch is learning, all it does is tell us what order to look at the points in. So for instance, maybe it learns a function, lexicographic order, that just goes 1, 2, 3, 4, 5, 6, 7, 8, 9. And so let's actually do this, because I feel like, in every math talk, you should actually do some math and not just talk about math. So ready, we're going to do it. OK, so our first point is that one in the upper left-hand corner. So we put it in. Great, that's in our set. Our second point is the next one. And we're going to put it in as long as it doesn't form an isosceles triangle. Well, I've only done 2 points, so I definitely haven't made an isosceles triangle yet. OK, so we put this in. Now I'm ready to put the third point in. And the next place I look is here. But that's not allowed. I want to emphasize, by the way, if you were like in grade school, you'd be like, that's not a triangle, that's a line segment. But we're mathematicians today, so the definition of an isosceles triangle is the 2 sides have the same length. So like 3 points, collinear points in arithmetic progression, that's an isosceles triangle by any right-thinking person's definition. So this is not allowed, so we got to skip it. And then we move on. OK, now does everybody understand the game? OK, so what's next? What happens here? Not allowed. Yeah, I got to skip it. What about here? No, what about here? Yeah, that's good. OK, good. OK, what's the next point that I put in? Yeah, exactly. I can't do this because that would make an isosceles with these guys. This guy is ruled out by this would form an isosceles triangle, but this is OK. And then I get a set. And in fact, you can convince yourself, it's not that hard, that actually 4 is the best you can do on the 3x3 grid. So this would be an example of a successful function. And so what happens is like literally FunSearch is evolving and evolving and learning like lots of real valued functions on this grid. And for each one, it's running this greedy algorithm. And now you see why I already forgot about, you asked about the hard versus soft constraint. So the way this is set up, it's automatically a hard constraint because it's automatically producing something with
An entropy or a distribution at each end, and maybe use that to help you, right? I like free energies. I'm a statistical physicist, right? That's the.
Yeah, so the nature of this kind of project, let me kind of like pull aside the curtain and sort of say, because the nature of being a pure mathematician and working with folks inside DeepMind and this kind of thing is that all of our meetings were like me saying like, well, could you do this and could you do that? So this kind of thing is the result of trying lots and lots and lots of things, all of which seemed like good ideas. Most of them don't work.
So that's the mystery, right? Like why this works.
I mean, I would say, unless my colleagues at DeepMind were hiding it from me, they don't know either. I think people don't have good intuition for this kind of problem of like what kinds of things were going to work. We just tried tons and tons and tons of stuff, and this worked best. I will say, for the pure mathematicians in the room, one thing I was sure was going to work was, we talk a lot about like symmetries of the problem. I'm like, well, okay, this problem has natural symmetries, and we should like build in functions that like respect those symmetries because they're sure to be natural. It actually hurt performance. It was very hurtful to my feelings as a pure mathematician. I'm gonna use my domain knowledge. I worked on this problem for a long time. It did not help, and actually somewhat hurt. So
At school, I read one of Martin Gardner's books, which talked about the problem of how many knights you can put on a square board, no two attack each other. And at one point, there was a point that this is a solution that should not exist because unlike all of the other beautifully symmetric ones, it was completely random looking, but it had more knights than was known to do otherwise.
yeah, so it's a great example. Sometimes if the problem is symmetric, we might expect the optimum to be symmetric, but there's no proof that that's true. And sometimes that kind of thing is true, and sometimes it's not. What can you do? Wait, this fell out of question first. Yes.
Yeah, usually in combinatorics, we can either take a constructive approach as you're taking here and like putting the points, or we can take like a destructive approach and we start with all the points and try to do the reverse. From the perspective of your machine learning model, are those two equivalent, or one is much better than the other, or?
So great question, and by great, I mean I know the answer. Which is that in the paper, I'm not going to really talk about today, but in a follow-up, in the paper that I wrote with Drew Sutherland, he's not here today, but he's been around, if you just search for my name and generative something, I think you'll find that paper. For the no isosceles problem, we did try the upside down remove things, and it works way worse. Can I tell you why? No, but it definitely works way worse than adding from the empty set works way better than subtracting from the full set. Again, I have no explanation for this. We were like, well, this might work. Doesn't work. Okay. I mean, this whole subject is like one big shrug emoji somehow. And okay. So I just want to emphasize how weird of a strategy this priority function is, because basically you're laying down these points in this greedy way. You're not doing anything. You're not doing any looking ahead. You're not doing anything intelligent about where should I put them so as not to like leave more space for future points. It's literally the same thing as if you built a chess engine where you listed all possible legal moves from any board position and put them all in order. And then at each stage, you were like, I'm going to play the highest ranking move that I'm allowed to play from this board position. And I truly believe you could not write a good chess engine that worked this way. And maybe I'm wrong, but I don't play chess. But I don't think that would work. So I just want to emphasize that this is like this constraint seems too strong. But it works pretty well. And to some extent, it may just be that less constrained versions of this wander too much. And there's some kind of trade-off between how much you constrain the programs you're allowed to search, and that channels it more and allows it to evolve, and more freedom, which you might think would be better because you have a bigger class of programs to search. You just wander aimlessly. And again, I think I only know how to explore this trade-off by trying different stuff problem by problem. But also because I'm an optimist, as Mark always accuses me of being, and I'm a theoretician, I sort of feel like eventually we'll have some intuition for this. We will get better at this. We just started, for God's sake. So I think.
Like I can imagine starting this for your original list of 10 to the 6 algorithms.
Mm-hmm.
But are you saying when you asked the LLM, you said generate more stuff subject to this constraint?
No. Oh, this is so important. Thank you for asking this, because this entire approach relies on one hypothesis about how the world works. which it turns out seems to be at least in some measure correct, which is that if you have some set of programs which perform well for this task, then they have something in common which the LLM can pick out. But you don't tell it, I'm trying to make sense with it. You don't tell it what's good about them. You don't tell it how it was selected. You literally just agnostically say, here's a bunch of programs. Give me more like these. You never state the objective. The objective is hidden from the LLM, and it's only seen in the evaluation step. That's sort of, I think that's part of the AlphaZero philosophy, where you're really trying to sort of not to cheat and let information leak in, and you're just saying the rules of the game are there's an oracular scoring function that tells you how good a program is, and all you're allowed to do is be given the high scores and then try to make more like that.
But I'm just trying to understand, what does it mean that it's best to search? Like, did you stay within this class of algorithms?
Yeah, because the way it's set up is the class of functions it's allowed to learn are functions that assign a real number to each one of these things, and then the part where you actually run this greedy algorithm is not learned. That part's fixed and that part's frozen. Like the way you evaluate a given priority function is you run a greedy algorithm with the points in that order.
Okay, just talking about priority.
Yeah, you're just in Marcus's swarm metaphor. It's like you're freezing all the bees except like one or two, and like they're allowed to evolve and somehow. Okay.
Oh, very. Sorry.
Yeah.
In practice, how do you actually give the program to the LLM? Like, is it like, okay, here's program 1, program 2, blend them? Like,
Yeah. So in this case, what seems to work best is pairs. So we mate them in pairs, which is a very traditional kind of thing to do in a genetic algorithm.
it's not like you learn an embedding of one program to the other and asking to combine it. It's really looking at program prompt.
Yeah, the program is a problem. Right. So another thing you could say, if you have some crazy manifold, you could sort of embed each one as a point in Rn and then literally take the midpoint of those two and then sort of decode that into a program. But we don't do that. We're literally, and maybe again, one of the things we talked about on the panel yesterday, and that I'm like constantly pitching is, this particular project, I did with DeepMind with access to all of their resources. I want to emphasize that the LLM step, we've never seen it matter very much which LLM you use. So I don't think this kind of work requires that you have like the latest and greatest frontier model. And if you run experiments like this, I want to encourage you to run it on like very cheap LLMs. Like, I think there's some things that really do take serious money, serious compute, serious resources. As somebody who wants like scientists like just out in the world to be able to like do stuff like on their laptops and run stuff, I want to emphasize that this kind of thing, you have to have access to somebody's LLM, but you can like, I do API calls and they're like very cheap and I can sort of spend all day doing these experiments and spend like $10. So
just can I clarify? I'm not quite sure I get it yet, but maybe I do. So is what you're doing, you're taking some vanilla LLM, let's say ChatGPT 3 or something, I think Matt is saying, and you say to the LLM, make me a Python program like these two programs.
yes,
That's all you do.
but we do it like thousands and thousands of times, but
Yeah,
yes.
that's all you do once, then you do it again.
Yeah.
Okay.
I was like, that cartoon really was it. I mean, yeah.
Yeah, I mean, so actually it does matter which language you're using, which LLM you're using, precisely because you don't need a good one. So if you want to have a search, explore the search space as quick as possible, you want a cheap LLM.
Yes, that's a great point. Right, right. Yeah.
The second thing that you actually give instruction, you don't just say, give me a program that looks like that. You have different instructions and you're going to change the instruction. Sometimes you say, try your best, or sometimes you say, oh, try something crazy now. And that just, and it gets a lot of this kind of prompt to kind of explore better the space.
Yes, that's absolutely true. So I should have said there is a certain amount of prompt engineering where like, I think in this particular paper, I think we often said like, don't change it too much. We said, and we actually asked it to keep the programs short. We didn't have to do that. I mean, but that's why. So I think again, that's a hyperparameter too, like sort of how exactly do you prompt it? Yeah.
I was going to ask you about these other parameters that API calls usually have, which actually tune how much exploratory the response is going to be.
Temperature or something, or like.
Do you explore that? Like, does it help?
I'm trying to remember in the paper with Drew. I don't think we changed that one, but I truly don't remember. Yeah, I mean, honestly, literally the nature of doing this kind of work is that there's like 1,000 things you could do, and then like you do however many you do in a certain amount of time, and then you post, and then you sort of try more stuff. So I don't think we've ever tried manually changing the temperature, but one certainly could, and one could see how or if that affects performance. Okay, but let me say, I want to say one other thing, which maybe hopefully is like a lingering question in people's minds, which is that like, why would we do it this crazy way? This is very important, so I want to like I want to get to this because when you are looking at a program, that is vastly more interpretable than looking at a set of points, right? That's so the reason I showed you those sets of points at the beginning is precisely because you probably did not learn very much from them. And in particular, looking at the sets of points in 6x6 and 7x7 definitely did not tell you how to make that set of points in 52x52. A program is different. A program produced by an LLM is designed to look like programs that people actually write, which means the programs that people to some extent can actually read. And so one of the motivations for doing it in this sort of cockamamie way is that you hope to actually generate something from which you can get an idea. Which is different from a large set of points in a grid, and for that matter is different from a very long formal proof in Lean, which even as a pure mathematician, I can't really read, to be honest, and it's very hard for me to draw ideas from it. So again, here I'm sort of speaking to like the mathematician's value system, which is that in the end, you know, the world doesn't depend on whether I make that set a little bit bigger or not, and like Google doesn't make any more or less money depending on whether that set is any bigger or not. I mean, we're doing it because we're trying to understand something about combinatorics. So in some sense, the goal is sort of not to have the biggest set. Like the goal is to sort of understand something about the geometry of points in the plane. And I think the programs give you like a lot better hope of getting that. So let me go and give you one example from the newer paper just to show what that looks like. Also because I think it's good for if you haven't seen it, just to see like what a chunk of LLM generated code looks like. And you don't have to like literally read this code. It says whatever it says. But the only thing I want to point out here is that on the bottom of your screen, I don't know if this is readable in the back, this priority function it gives something very familiar, like an x squared plus y squared, and then maybe times some small constant or whatever, to the 0.5 power, square root. Okay, so square root of x squared plus y squared is certainly a function that appears in like lots of codes, but it's not so surprising that it appears. But what is it measuring? It's measuring distance from the center of the square. I will now show you a picture, and this is a picture from the more recent paper that I wrote with my student Karan Srivastava and Drew and Kit Fraser-Taliente. So here, this heat map is showing you this real valued function on a big 52x52 grid. Blue is like the lowest priority. The warmer colors are higher priority. Those are better. So what this is telling you is when you lay down the points on your grid, you really want to start from the outside. You really want to prioritize the points that are near the edge. And this function in this case is like only a very small perturbation of like pure distance from the center. It's like almost just that. So from this, you're actually learning something, right? It's telling you, oh, what it's learning is that when you try to make a large subset like this, you should prioritize points that are farther from the edge. Now, 2 comments on this. One, I will admit we already knew this because we generated some big examples with like stat solvers and more traditional methods. And you can pretty much see, even if you look at good examples in like 10x10 or 20x20 that you make by traditional means, you see that they cluster around the edges. So we did know that. On the other hand, and that's point 1. And point 2 is that then if you sort of think about it as a combinatorist, you start to realize why that's a good idea. I'm not going to, when it's not a math talk, so I'm not going to talk about it, but it's not so hard to convince yourself, oh yeah, I see why under any reasonable heuristic, I would expect to be able to do better if I stay away from the center. That said, I want to emphasize that the machine just automatically learns this. And it learns it in an interpretable way. It learns it not because you like look at the pictures and sort of can figure it out, but because you like literally look at the function and it's saying, I'm punishing you for being close to the center and I'm rewarding you for being far away. So I think in some sense, at least for me, one of the cool things about doing it this way is that it points to something which is like, you know, one of my big hopes for the interaction of mathematics and machine learning, which is that there's an iteration between human and machine, where just as has happened with every other incursion of technology into mathematics, like we use the output of the machine to help us get new ideas. So maybe in that respect, now, okay, one thing you might say is like, here's what would be really great. What would be really great is if it generates this program, and then at the beginning of the program it says n equals 52, and then you're like, oh, well, now that I have the program, I'm just going to change it to say like n equals 552, and get the best known example. If that worked, I would be giving a talk about that. And unfortunately, at present, we have never seen this work. It's too bad. So this sort of speaks to your question, Mark. It does not, at present, seem to generalize very well from the instances it was trained on to others. On the other hand, so maybe I'll just sort of say this as like a little slogan. In this long paper that we wrote, to me, the most interesting thing in it is not in the main body of the paper. It's actually in the supplement. And it has to do with a problem that, for reasons of time, I'm not even going to try to describe, but it has to do with computing the Shannon capacity of a graph, which is like a well-known hard problem in combinatorics. We were trying to get lower bounds for that, which is something else you can do by producing interesting combinatorial examples. And there was one example for the 7 cycle, an example of a very simple graph where we don't actually know the Shannon capacity. And the program was so simple and so nice that I was like, I'm going to figure out like why does that work? I got to figure out what it's doing. And actually, that one program, after reading it and thinking about it, I was able to see like, oh, this gives a general lower bound for the n cycle. Now that I see what it's doing, it was sort of a very clever thing involving like writing 7 in binary. I was like, oh, I can see how to extend this. Now, once I understood what it was doing, then I was able to find it. Like that argument existed. It existed in like a paper from the 70s. But first of all, I don't think it came to that. I mean, I can't prove this. I don't think it came to that because somehow the Python code generating LLM was like reading like old math papers in PDF from the 70s. I actually don't. I can't say that's impossible. I don't really think that's true. I think it's just the case that this is like an example of something that I expect to be happening more frequently, where we will do experiments like this and we'll generate things, whether examples or code that generates examples, and that will allow humans seeing, oh, this works surprisingly well, to like read it and understand why it's working well and use that to bootstrap and generalize. So in this case, it was something that was written down in the 1970s, but that was like already 20 years after the problem was formulated. So I think that's kind of a proof of concept. So to sum up, and then I'll sort of have some closing words. So this method and methods like it can, when you train on a certain problem class, sometimes, not every time, but with alpha evolve, we see it happening in like dozens and dozens of times, generate examples that do better than we were able to do on our own for particular problems. What they don't do at present is produce general algorithms where the program, you run it for any n, and it always gives you the best known thing, which would be sort of somehow the holy grail. But I think this intermediate space is one that's extremely interesting for mathematics, this space where the machine doesn't do it on its own, but it gives us ideas. It's a source of inspiration for human mathematicians. So let me close.
Just didn't select for it. Couldn't you imagine you just select for things that give you the least number of isosceles when I double n or something? But I feel like the problem is in the have you tried actually selecting for things that generalize?
Great question. Also, we've tried it. Right now, doesn't work. So right now, that is absolutely, you guys should all be doing experiments like this because you were asking exactly the right questions. But like, if you train on a bunch of different n's trying to kind of reward things that generalize well and are not single n specific, at least in every case I've seen, what happens is it does worse for n than the ones trained specifically on n, and it sort of does okay on the interval when you train, and then it falls off just as fast as if you trained on one. So I wanted that to work. I don't have a good explanation for, I mean, okay, shrug emoji. Okay, so a few questions to end with about where we're going from here. So one thing, and one reason that I'm sort of pushing this notion of what can we do cheaply is, I do somehow worry about like, what if there's certain kinds of math that we want to do that we can really only do if we have like extremely expensive specialized equipment that like only a few big companies or maybe national governments have. If that's what it is, then that's what it is. Like, that's not up to me. That's a question about like what math is like and what computation is like. I just think sort of sociologically we should be ready for it. And I will say, I've used this slide several times before because I knew I was going to put up this slide. I actually talked with a bunch of physicists, because a bunch of physicists around here, they're among you, in case you didn't know that. And I would say, Mike, you can back me up on this. I don't think the physicists think it's as big of a problem as I would have perceived it to be. So maybe the super collider problem is not such a bad problem to have. Oh, okay. So there's where I'm going to fight about this. Okay. So maybe instead of just being like, this is something I worry about, maybe I'll say as mathematicians, I hope we can learn from the physicists about how to mitigate this problem if indeed it does develop for us, if there's certain kinds of research that we want to do. But I will say one of the things that people have told me this week is like, well, to some extent, yes, but maybe it sort of shifts some energy into parts of physics where you don't need the super collider. So, I mean, maybe that's one reason I'm sort of talking about there's things where you need massive compute, but there's also really interesting things you can do where you don't, and maybe sort of somehow energy will flow there. But let me also say, because I already forgot, was it you, Nick, who brought up counterexamples at the very beginning? I mean, one of the most important types of examples is a counterexample, and in some sense I want to, Adam Wagner, who's now at DeepMind, was like one of the people who first got me into this. He wrote this wonderful paper, pre-transformers, by the way, just like a sort of standard like RNN paper, where he just took like a bunch of conjectures that were in the literature and graph theory and was like, well, here's counterexamples, 16 of them. We write down a lot of conjectures in math, and we often write down a conjecture just because we can't think of any reason for it to be false. I think we can improve our sort of conjecturing hygiene practices a lot in math, and I think this is like a great way to put pressure on our conjecture. So my former grad student Eric Ramos was here earlier this week and he gave a wonderful talk where there was this one actually was a conjecture of Erdős, a conjecture about independent numbers of trees, which no counterexample to this was found until like 2023. Eric and his group found like tens of thousands of counterexamples, and like on a laptop with one GPU. So this is a good example of like there's like lots of stuff we can do that's gonna like in this particular case, somebody came up with an example 2 years ago, but that might not have happened, right? So I think we're in a position to actually really do things that are of material importance for math cheaply, quickly, and we should be doing that. Yeah.
Like, did it feel any sort of blind spot that the community has, or were they all just sort of esoteric, random things with no connections?
So yes, but we don't understand why. So for instance, his counterexamples, there was a counterexample that a certain sequence is always what's called log concave, which is something you check at each point in the sequence. His counterexamples were all counterexamples at the exact same point of the sequence, and when he tried to get the machine to find counterexamples at other points, it didn't find any. Now we actually do know by these people that there are counterexamples at these other points. And again, shrug emoji, the FunSearch finds the ones at this one point, and it not only does it find the ones that were already known, it finds tens of thousands of them. And then when you try to get it to look for counterexamples at these other points where we know they exist, it finds zero. So yes, but this is an important question because yes, there are patterns, but we don't actually know whether the patterns are the patterns of mathematical reality or the patterns of what kinds of things this particular implementation of this particular machine can find.
Saying about conjectures, right? Because they're sort of, they say something about the psychology of the community, right? It's sort of like, these are things that we believe to be true, but we can't really prove it. But it's probably, it says something, right, about like the community. And so I think it's an interesting approach to like try to find counterexamples to these conjectures and then what that would say about the mathematical community.
I like the way you said it says something about the community, but you didn't say whether it was like something bad or something good. You were like, let's just say it's characterizing.
There's just like a specific kind of example that we can't think of, right? Like there's some sort of psychological reason, or is it like they're all just sort of weird esoteric things, and so it's like you would need a machine to find the counterexample, or like it says something, right? It's
that before. So I mean, one way of thinking of these is they are, they're very fast, very eccentric searchers. And we talk a lot about the question of at what point, what does it mean for machines to, like, I think super intelligent was the word that Marcus used, or superhuman or whatever. I mean, there's lots of directions in which they're already superhuman. I mean, certainly in terms of like multiplying large numbers, already superhuman performance, right? And here too, this is like sort of a new zone of human performance where we're like sort of patiently looking for counterexamples in an interesting way. I would say that in some sense, we have like superhuman performance in that very specific cognitive direction, and that's kind of what's going on here. So let me close. I'm going to say two slightly salty slides, which are going to sound more salty than they are because I mean them in an optimistic way. So Mark, I'm going to put up the slide that I said I wasn't going to put up. So okay, so here's one slide, which is just in some sense repeating what I said, in that I worked on the CAPSET problem for a long time. I do think it's cool to improve on the best possible CAPSET. But in some sense, I think a lot of the gain to mathematics, I think there's a huge amount to be gained from things like what I just said, being better about making conjectures, being better about generating information that gives us ideas. And I think a lot of that gain is going to come on problems that are not problems with like decades of literature that people have worked very hard on in some sense. I think we're going to get more out of problems that people have not thought that much about, but which we actually want to know the answers to, and we can sort of use this at a more initial process of our thinking about the problems. So the problems, or maybe they're hard and maybe they're easy, and this sort of helps us start to find out what's easy. So I don't want to. I mean, it's so, we live in this kind of like Olympics, like gold medal culture. But there's really something to be gained by getting much better and faster and more efficient at doing things that are like maybe turn out not to be too hard. So like here's my really salty slide. So this is something I kind of believe about AI the way it is at present. And I think I put it up there because it sounds like an insult, but it's meant to be a great compliment. I think mediocre performance, and if I were to make a less salty version of this slide, I would say reasonable competence at scale, right? That would be a way to say it that would not like raise people's hackles as much. But like, mediocre performance is extremely valuable, especially if you have a lot of it. I mean, we are all sub-mediocre at most things that we might be asked to do. So I think that, this ability to think of some, I mean, this happens all the time. Any working mathematician knows this. You think of things all the time and you're like, I wonder if, and like, okay, I don't really have time to think about that, or I just haven't thought about it very hard, or maybe you use stuff from a field I don't know. So I think like having these tools, which are certainly at the moment sort of not better than an expert at the field, but maybe like better than me, and just having like, if we can sort of build broad, fast, reliable access to those tools, I really think that's going to be quite, I think mediocrity at scale, I think will be very valuable to mathematics, and we should applaud it. So I'm going to stop there. Thank you guys so much.